Right, in this video, I'm going to teach you the integral test. I've actually written it out here. This is a less formal way of saying it, but it's what makes sense to me, and I think it's a good way to say it to help you understand it. I'm going to go over what I'm saying here. I'm going to do two examples, and then I am going to show you why it's true. And if we have time, we'll do the P-series test in this video as well. That might be in the next video. Okay, so what the integral test says is this will tell me, it will determine if an integral converges, or sorry, if a series converges or diverges. It doesn't work with all series, but this is different from the nth term test that we did a moment ago, because the nth term test will only tell me if something diverges. This one will tell me both if it's conclusive. And I think you'll see cases where it is inconclusive. But what the integral test says is that if I have a series and there is a corresponding integral, and I'll show you what I mean by that in the examples, then what I've got here is they do the same thing. If the integral converges, then the series converges. If the integral diverges, then the series diverges. And the explanation is pretty fluid, so I think it'll make sense. But before I do my explanation, I'm going to do two examples for you. First one, example one. I'm going to say S sub infinity is sigma n equal 1 to infinity of 1 over n squared. What would that be? It would be 1 over 1 squared, which is 1, plus 1 over 4, because that's 2 squared, plus 1 over 9, plus 1 over 16, plus go on for forever. Okay, so what is the corresponding integral? Well, in this case, I should add, I said this in one of the earlier videos, but I don't have to have this start at 1. I can start at a different index, that is fine, but frequently they often either start at 1 or at 0. This one couldn't start at 0 because it would give me a 0 in the denominator. Anyway, so the question then becomes, what is the corresponding integral that would go with this? Well, it would be the integral from 1 out to infinity of, I'm just going to do 1 over n squared, but with x's. So what do I get? 1 over x squared dx. Now, I'm not going to calculate this integral because in the previous video, we did this, right? Do we have 1 over n squared up here? We don't have it up here, but remember, if the power in the denominator here was bigger than 1, or I should say it was 1 or bigger, right? Sorry, if the denominator was bigger than 1, the power, then the integral converges, right? So we know this converges by the logic of the previous video that I just did and that you should have just watched. So this converges, write an equal sign. That one converges. So S sub infinity also converges. They're not going to converge to the same thing. I'm not telling you what these numbers 1 plus 1/4 plus 1/9 plus 1/16 da 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 for forever. I'm not telling you what they add to, like I could do with this integral. I could actually calculate this integral, but I am saying that it will converge, and that's the tool that we need to be able to do what we're going to do when we use these things for approximations. Before I go into example 2, I want to talk about a couple things. One, I typically like to, within a problem, identify that sigma as S sub infinity so that I can talk about it down here without having to write it out. I don't like using the word it because it's unclear, especially as we move on and we're dealing with multiple ones of these at the same time. So I say S sub infinity converges after having identified that this is S sub infinity. The other way to do it would be to rewrite this entire thing right there. Second thing, in order to formally do the integral test, you need to actually show that these integrals converge, right? So if I gave you one that was something else that we hadn't just talked about, right? Like we did right here. Say I gave you, I guess we'll call this example 2. I'm not going to complete it, but I'm using it as an example of when we would need to actually do work. So say this was our series that we were trying to figure out, all right, does this converge or not? Well, I would go and use this integral, and then you have to actually calculate and show that it converges. And then we could say, all right, that means that this series converges as well. Since we just did it for this one, I'm not going to do it. I'm not going to show that it converges. I'm demonstrating this test to you. All right, so let's do example 3. Here we go. Example 3. One thing I forgot. So converges by the integral test. It's always good to say what test you're using whenever you're making these conclusions. All right, so example 3. Let's take sigma n equals 1 to infinity of 1 over root n. So I would like you to try to do as much work as I did here for this one, right? Then I actually write the terms out, write the first 4 terms out, just so you can visualize what's going on with this thing. And then use the ideas that we had in the last video in terms of when things converge or diverge. Okay, I wrote S sub infinity, so I could talk about it later, easier. I wrote out the first 4 terms, 1 plus 1 over root 2, 1 over root 3, 1 over root 4. And then I wrote the integral, the corresponding integral. Integral from 1 to infinity of 1 over root x dx. Well, again, this is one that we just did up here, right? You know, this one fell into this category of diverges, right? So, that integral diverges, so S sub infinity also diverges by the integral test. Let's do one more. So we're going to do this one out completely, so that you can see a model of what it looks like to do the integral test completely. So I'm going to do sigma n equals 1 to infinity of 1 over e to the 2n. Does it converge or does it diverge? Now, as with a lot of these series, there are actually multiple tests that will work with this one. You have previously done geometric series from your experience in pre-calc or your crash course in pre-calculus, or pre-calculus series. So this is actually a geometric series, but I'm going to look at it from the integral test perspective. So let's see if you can pause and set up the integral that corresponds with this. Okay, hopefully you wrote that. Now, this is like messy, and we don't like it the way it is. So what we're going to do is change its form, and maybe you already see how to change its form. I am going to write integral 1 to infinity of that e to the 2x in the denominator. So what I can do is write it as e to the negative 2x dx like this. And now this becomes something that I can integrate. So this is the limit as b goes to infinity of, I'm going to integrate e to the negative 2x. That gives me a negative 1/2 e to the negative 2x. And then I'm going to evaluate it from 1 out to b. And then that gives me the limit as b goes to infinity of, all right, I got negative 1/2 e to the negative 2b. That's the upper bound. Minus a negative gives me a double negative half e to the negative 2 times 1. So from here, all right, I got to do this limit. This doesn't have to be, so it's just going to stay the same. And then this right here, it's exponential decay. We know that exponential decay functions go to 0. So the limit, this part of the limit right here, that goes to 0. I hope you see that. You should see that with your experience in math so far. So what do we get when we do this limit? We get 0. That's the highlighted circle part there. Plus 1/2, whoops, I'm thinking and writing at the same time, e to the -2. We could write this as 1 over 2e squared. But listen, bottom line is that this integral doesn't go to infinity. It doesn't diverge. It converges. Since the integral, the corresponding integral to the series converges, the series also converges. So here's where I'm going to go back in here and squeeze in s sub infinity. And then I'm going to say, since the integral converges, s sub infinity also converges by the integral test. And that's a completely done integral test problem. Start with the series, figure out what integral it would be, do the integration, and then get to either that the integral converges or diverges. This is an important piece right here. And then just make your statement at the end. You may be like, sweet, we can do all series, right? But unfortunately, many of the series that come up are not integratable at this point, so we need some more tools. Additionally, this example 1 and the example 2 paired with what we did in the previous video with these things converging or diverging based on the p-value, that is going to play a role in where we're going next with this, which is called the p-series test. And that thing is crazy important, crazy useful. We use it all the time, and it will be in our next video. I hope this is making some sense, and I will see you soon. Bye.